And I'm very pleased to welcome Leo Trukšāns, leading QKD specialist for LVRTC. And he will speak about LatQN practical outcomes. Leo, where are you? Yes. Perfect. A nice applause. The stage is yours.
Thank you. So yes, I'm going to talk about this project that we call LatQN, which means Latvian National Quantum Network. And I will first start with some theory about quantum key distribution and the problem with asymmetric cryptography. The theory, probably all of you know, but to remind you, then few words about the structure of our project, and then I will finally focus on the practical outcomes. So what are we going to get when the project ends? And actually we have already first results early in the project. So yes, so this is the project funded by European Union and also organizations in Latvia. And so the main goal is basically to build the first national quantum communication infrastructure. And there are 4 partners. The main partner is LVRTC, which is a Latvian state radio and television company, center. Which actually is also nowadays quite large infrastructure and data center operator and significant help for government organizations, public organizations, providing security solutions and infrastructure. The leading partner, and then 3 other partners. So Valsts, which is basically the electronic monitoring organization, and they have taken the responsibility for activity to try QKD systems in mobile infrastructure. Since with 5G we are moving a lot of computing into, well, at least we will be moving into base stations closer to the edge, to users. So yeah, some perhaps important processing going on there as well. LUMI, the Institute of Computer Science and Mathematics of University of Latvia. They have some early experience with QKD systems and quite good at theoretical algorithms for post-quantum computing. And then TET, which has taken activity for trying QKD in some use cases. The project will go for 2.5 years. And I will later speak about the practical outcomes. Now, a few minutes about the theory. This is already widely known around the world, but I will try to take some minutes from you and review this. So before I get into QKD, I would like to remind that a lot of current encrypted communication over internet is based on both major encryption algorithm paradigms, the symmetric cryptography and asymmetric cryptography. And both of them are used for its own purposes, symmetric for the actual stream encryption, stream of data, and asymmetric for things like negotiating symmetric keys, authentication, electronic signatures, and so on. And all of that works very well. Asymmetric is very helpful for expromptum communication between subjects that never have been dealing before. There is a problem with asymmetric cryptography. The algorithms that we use today are based on one of the 2 hard mathematical problems, the factorization and discrete logarithm. And those are very good problems in some sense, because for defense you need to do very little to make attackers' prospects impossible, basically. Just increasing asymmetric key, let's say by 2, you increase the amount of possible combinations so much that the attackers simply don't even try it anymore. But with quantum algorithms, they are also very good at scaling to a large number of combinations. So basically with quantum computers, we will not have that luxury anymore that we simply increase key twice the size of the key and they fail. They will not fail for increasing asymmetric key by a factor of 2. The attacker will need just a quantum computer whose size is increased by 2, basically twice bigger computer, which is a matter of very close future. So that means that asymmetric cryptography that we know before will be quite useless in some years to come when those big enough quantum computers will become available. So there are 2 strategies how the world is dealing with this, and really very different. One of them is try to come up with better asymmetric algorithms that would be resistible to quantum computers. And there is some work, and of course the world is paying attention to this. A lot of bright minds have come together to propose better algorithms. The American National Institute of Science and Technology is taking leading role in making a competition for such algorithm, but there is still a lot of work to do. If that would be solved, let's say a replacement for RSA that is resistible to quantum, that would solve a lot of problems for the future, but we still don't have such a solution. So the other strategy is let's try to use the power of quantum technologies and the specifics of quantum physics to come up with technology that would be resistible for technology to encrypt data channel that would be resistible to quantum computers. And a lot of attention has been put into this actually for decades already. The picture that you see here with Alice and Bob and some arrows in between is actually showing an algorithm that is called BB84, which is one of the best QKD algorithms that we know today. And it was actually theoretically proposed already in 1984. Yes, 84. And I will not try to describe this. There's, like I said, a lot of information and very good descriptions around it. And after all, if anything fails, just ask ChatGPT. It probably will also explain it quite well. But the result is that those 2 persons, Alice and Bob, can negotiate a symmetric key without using asymmetric cryptography. That's how we do it today. But they don't rely on asymmetric anymore because that will be breakable by quantum. So they negotiate, and they negotiate the key in such a way that first there is a guarantee that no one has seen it along the way. And the other is that even if someone is eavesdropping, the eavesdropper is detectable. Basically, what happens when eavesdropper tries to listen on this channel, the detectors at the other end, the Bob, Alice is transmitter, Bob is receiver, the Bob basically gets errors. Synchronization simply doesn't proceed if there is an eavesdropper. Very interesting technology. Currently, it is still in its early commercial stages. It's been available in commercial products for approximately 5 years, more or less ready, but it is evolving quite fast. So in 2021, we did an experiment and a successful communication line of QKD in LVRTC infrastructure for 33 kilometers long distance. That was a record. Before that, we did it at LMT, optical infrastructure, that was 12 kilometers. And to my knowledge, that's the record so far. Of course, in other countries, we have longer distances, the countries that have more of this equipment and have started doing this before us. So when we get to the actual new equipment, I'm 100% sure we will break this record in Latvia as well. But most importantly, then, 2 years back, we demonstrated two possibilities that we can do. First, we can run QKD in real Latvian infrastructure. It's actually far from plug and play. As you know it, it is an achievement. And also, we actually showed a complete system with two encryptors, I and Brancis, taking keys from Alice and Bob and using symmetric cryptography to encrypt and demonstrate a working data channel that is encrypted with quantum key distribution, synchronized keys. So basically, a solution that is ready for future when quantum starts to break things. So we started this project early this year, and we are aiming at not only gains of experience and competence, which is an important factor. Those 4 partners definitely will get more experience, understanding, and practical skills, know-how, how to use this technology, how to integrate it. And this is also very important for such a new and still a bit green technology. But we also will make some lasting commitments. We will build some production parts of the network. Yeah, so let's go on. So the test bed, that's the network that will be available for partners, or also for researchers, basically for everyone in Latvia who would like to try things out with this new technology. The test bed will be a triangle network consisting of 3 links. And what's interesting, each of the links will be from a different partner. So we will also test how such a system actually works in real life, because the most important benefit of QKD network is actually trust. That you do not lose keys, that keys are available only to the I and Brancis. So we will try that out, how it works, how the communication, how the integration works with encryptors. Yes, so that will be the test bed. We are welcoming everyone, basically, in Latvia to come to us if it seems interesting to try integrations and perhaps build new products on top of such a system. In few slides, I will show how using QKD network looks in topology. So some other activities we are going to do in the project. So we will try this QKD in some sectors that would really love to have. higher security perhaps than we would do it at household, like finance, like healthcare, and so on. Of course, the defense sector. Yeah, and we are also looking for partners in the future to integrate into European network. There is already an activity called EuroQCI. So to build quantum cryptography infrastructure, quantum communication infrastructure on continent-wide scale. This is technically challenging because current terrestrial optical QKD products reach only approximately 150 kilometers away. So with neighboring countries in the Baltic states, yes, coming closer together to the border, we can still build pan-Baltic quantum network, but further countries are out of reach of current technology. Satellites come to rescue. Yes, you can send those short pulses of light, not only through optical lines, but also through the air to satellite and back to ground station. Using that technology, it's more expensive and difficult, but using that one, we could already reach practically all Europe. Perhaps European partner countries that are further away from us, ahead of us in this aspect, like Austria, Netherlands, and so on. Anyway, we are already participating in the brainstorms, in workshops, sessions with possible partners, and we are looking forward to integrate our national quantum communication infrastructure into wider European infrastructure later. Perhaps a few years from now. So let me tell you about how to use QKD. So that would be one of my, I don't know, maybe main topics for today. So we know already the theory, we know the challenges and so on, but how it will look like when we have this system and how to use it. So like I said, basically what QKD does is synchronizes symmetric keys in a trustworthy way. Keys is what those devices give out to you. Basically, you can imagine you have one QKD device on one end of the line, the other device on the other end, and both of these boxes give out keys. Keys that are synchronized with this very advanced and secure QKD technology. So whom do they give those keys to? They give to secure applications. And here you see some terminology. So the key management entities, those are the services that give out the keys. And secure application entities, size, those are the ones that will consume the keys. And what they are using those keys for is really up to application. Here in this picture, I draw two routers. And this is type of integration that, like I said, we already demonstrated 2 years back. So I is getting keys from QKD device Alice, and Brents is taking from Bob. And they use IPsec tunnel in between. That's what we did 2 years back. So they create IPsec tunnel, and they do not even try to negotiate these symmetric keys using asymmetric cryptography like they would do now. They just take already synchronized keys at both ends. They just negotiate the key ID, because there's a lot of keys coming out of these boxes. They come with their own IDs. That's what they can agree on over public channel. No, nothing wrong with that. The key material itself, of course, is not revealed. So they already use this system. So you can use routers, encryptors, whatever you currently use for encrypting whole streams of data towards the other end. Towards the other end of the channel. But there can be other applications as well. It can be a mail system, for instance. It can be an instant messaging. It can be a web page. It can be an integrated web service, let's say two integrated information systems talking to each other. So it can be a lot of applications, actually, and that's why there is this term of application entity. Okay, because we often think of network encryption just in layer 2 or maybe few layers up, but so we can use those keys wherever we like. And I will also mention one of the corporations that we started. We can tell this is our first user when we still don't have a real network yet. So it's the company MikroTikls. You probably know that, at least in Latvia, we know. That's a network equipment manufacturer. You know, these devices are very high functionality devices, a lot of encapsulation technologies in there, and a lot of tunneling and encryption technologies. So we have started cooperation with them already now, middle of this year, and we will help them to implement QKD client, the secure application entity, into router's operating system. So if you're curious about how these devices come up and this functionality, when will it arrive, keep up with MikroTik news. I believe there will be announcement. I don't think it will be very soon, but it will be. And one more step that we didn't have it in project, but I believe it's a very good idea. So how to help MikroTikls and other companies like that develop QKD compatibility if we don't have, well, we have one pair that we started in 2019, but we don't have a spare pair, and also, well, basically we can't give them the boxes, the actual boxes. There is also this reason that we don't want to give out boxes to other users because there is a potential of compromising the system. Access from application to from site to KME is supposed to be in domain of secure infrastructure. Basically, the boxes need to be sitting very close with a direct cable, no way to come in between of them, okay? Yeah, so that's one of the reasons we don't give away boxes, and we don't allow remote access to them as well, of course. So how to help them? So we created this simulator, basically a software that works as a KME service, the Alice and the Bob. And we call the simulator Next Door Key, which is of course a reference to Smokey's song Living Next Door to Alice. So the simulator provides two services that behave the very same way as the actual QKD boxes themselves. They provide the same service. The most popular standard for key retrieval is HC014, and that's the protocol that we implemented there. So we can really give such a simulator to anyone, and they can start implementing the client side with the simulator. Later, just switch the simulator with the real box, and the protocol works the same. Okay, I believe I'm early. So Yeah, so that was the first cooperation that we have already during this year. And we look forward to very interesting 2 years ahead of us, and actually building the network, having these use cases, testing it in different applications, and building the trusted node, which is another topic that I don't have time for. So thank you.
Yeah. Okay, a nice applause, please. Yes, well, as you can see, we have quite a nice mix by the end of the day, you know, mingling together policies, NCCs, and quantum encryption. And obviously, there are some questions for you using Menti platform, and I would say they are all tough.
Okay.
But I will start with the toughest one. Yeah. Okay, you need to explain quantum cryptography to a 7-year-old.
Okay, not the post-quantum, but the QKD probably. Post-quantum.
It says quantum cryptography.
Quantum cryptography. Okay. So the post-quantum is basically that you have a very good tool that works very well for you, but there will come a time when this tool becomes useless. So you should be starting thinking about better tool. That's for encryption in this case, and that's what PQC is about. But the QKD strategy, well, using quantum physics to build a channel that cannot be eavesdropped.
Okay, I'm still not sure. As being 7-year-old, I quite get you. So, but this probably is much better. You already touched one of the vulnerabilities that and the reasons why you do not have or do not give access to the boxes, or do not have remote access, etc. Are there any other potential vulnerabilities or things people who will experiment with these things, experiment with the simulation, that they would need to know that are, potential hazards? So if simulator can simulate potential weaknesses, not sure about it, but we can probably build in vulnerabilities if we like, but with actual QKD devices, there is this debate, can these systems be compromised the very core of their functionality? So like I said, they negotiate keys so that you cannot eavesdrop. So people are really trying to attack this functionality. So can we actually eavesdrop? And then somehow they experiment with high energy light pulses, basically trying to, like a splash towards you, you get blind for a moment. They try to send pulses of light into these devices that they don't expect, and then try to get unexpected behavior out of them. That's attacking the QKD technology itself. But with the key service, you really need to be aware that don't allow anyone ever to connect to that port. That's only for you. You use a special laptop, clean install with no USB ever attached to it, and then connect with direct cable and nothing else ever. Okay. An easy one. How big is the device actually?
Yeah, how big it is. It's actually the ones that we had in 2019 still in Lumi. Those are the Clavis 3 from ID Quantic, the Swiss company, one of the 2 best manufacturers. It's like a desktop computer.
Okay.
You can put a monitor on it, but it's a QKD device.
Good. And the last question for you, how would VPNs work with that?
VPNs, well, very well. What we actually did 2 years back is we modified the IPsec VPN in Linux to not to use the keys that they usually negotiate, but basically to enforce them to use QKD keys. So the QKD is exactly very well suited for VPNs. Okay, so for VPN authentication, so the best authentication you have for VPNs right now is not the passwords, although a lot of, maybe not you, but a lot of organizations use passwords. The best one is certificates and asymmetric keys. So you will be able in the future to take keys from QKD and never even touch asymmetric algorithms at all. Okay, so that's the main reason for QKD. Let's forget asymmetric cryptography because it's vulnerable.
Good, good. Thank you so much.